So hello everyone, welcome to Chem Analysis. In today's lecture, I will solve previous year physical questions of CSIR-NET December 2017 and which question came for 2 marks. And in this video, I will solve 10 questions, among which few questions are easy and few questions are really tricky. So try to watch this video till the end so that you can't miss any question. So let's start it. The first question came from quantum chemistry and it is given that the commutator of A and B operator is equal to 0 and commutator of A and C operator is also equal to 0. Then we have to identify the necessary condition which holds for A, B and C operators. Now it is given that commutator of A and B is equal to 0 and commutator of A and C is equal to also 0. Now from these two conditions we have to see that among these four options which is possible. Now we can easily say that commutator of B and C is not 0 from these two conditions. So option number A is not correct. Now from the remaining three conditions, let's take this second condition, and from the rule of commutator of two multiplication operator, that is here we can see that B and C are multiplication. From this we can solve it like this one, that is we can write it from like this. That is, in the first condition we are bringing out B operator out of this commutator and we are writing this, since B is out of the commutator bracket, so it will remain as A and C commutator. And in the second case we can bring out this C operator out of the bracket, and since C is on the right side, so after bringing out the commutator bracket it will remain at the right side. And in this case, first case, is B in the multiplication is on the left side, so while bringing from the commutator bracket it will remain on the left side. Is it okay? Now here if we apply the given two condition, that is we can see here that is given A and C commutator is equal to 0, so this term will be 0, and in the second case A and B commutator is also given as 0, so in the second condition the term will be equal to 0, and we can see that this commutator is equal to 0, so this condition is satisfied. And if you apply the same rule for the remaining two cases, you will see that these two will not be equal to 0. Let's see for this one, you can write it like this. Here we can see that this commutator is not equal to 0. But this one B and A, since here is given commutator of A and B is equal to 0, so we can also take that commutator of B and A operator will be also 0. This term is 0, but this term is not equal to 0, so as a whole this term will be not equal to 0. And similarly you can apply the rule for this case, you will also get that this commutator will not be equal to 0. So you can say that option number 2 is the correct answer. So let's see next question. Here it is also from quantum chemistry and it is related to eigenvalue equation, and we have to identify the correct statement among the following given four options. And here it is given that A is a Hermitian operator, and from the condition of a Hermitian operator and the eigenvalue relation, the eigenfunction equation is, if a operator is A applied on a eigenfunction, if psi is a eigenfunction, then that will result with the same eigenfunction multiplied by a value, and this value is known as eigenvalue, and psi is eigenfunction. Now from the condition of a eigenfunction of a Hermitian operator, we can say that the eigenvalue corresponding to a Hermitian operator will be real, that is A will be real, and the value can be positive or negative, but it will be real, not complex number. And since the eigenvalue corresponding to Hermitian operator A is real, it can be positive or negative. If we consider the eigenvalue of A square operator, then it will must be positive. Since eigenvalue corresponding to A operator can be positive or negative, but the square of that operator must be positive. So the first option we can say it is not correct. For the second condition, the eigenvalues of A square are always positive, it is correct. And for the third condition, no eigenfunction of A is an eigenfunction of A square, it is also not correct. Since the eigenfunction of A, if psi is an eigenfunction of A, then psi can be eigenfunction of A square also. So this condition is also not correct, and the eigenvalues of A square can be complex, it is also not correct. Since eigenvalue corresponding to Hermitian operator A is real, so eigenvalues of A square must be a real value. So you can see that second option is correct answer. So this question came from group theory, and here we have to identify the molecule which contains a C2 axis of symmetry. Now if we see the structure or see the geometry of the given 4 compound, the BH2Cl will be trigonal planar molecule, and since it is a trigonal planar molecule, there will be C2 axis corresponding to this boron and chlorine center, and it will convert this hydrogen atom to on the other side, and this hydrogen atom will come at this place. So it contains one C2 axis. If we consider the other compound, CHCCl is pyramidal shape, it is tetrahedral, and this molecule does not contain any C2 axis. It contains a C3 axis of symmetry, but does not contain any C2 axis of symmetry. And similarly, NH2Cl, it is a pyramidal molecule, there will be one lone pair, it also does not contain any C2 axis. And for the last case, that is HOCl, it is V shaped, and there will be two lone pair, and it does not also contain any C2 axis. So option number A is the correct answer. Now the next question is little tricky question. We have to identify the molecule among these 4 which show Raman spectrum but not any IR spectrum. That means we have to identify the molecule which does not have any IR stretching bands but shows Raman stretching bands. Is it clear? Now the condition for a molecule to show IR stretching bands, that is the dipole moment corresponding to that molecule will not be equal to 0. That means the molecule should contain a dipole moment, or after the vibration there will be a change in the dipole moment of the molecule. Now for the first molecule we can see that it is a homodiatomic molecule, and the dipole moment corresponding to this molecule is 0, so it will be IR inactive. And the necessary condition for a molecule to show Raman activity is that there will be a polarizability induced within a molecule in a applied electrical field. Means if we place a molecule in a applied electrical field, then there will be a polarization within a bond in the molecule. Now if we place hydrogen molecule in an applied electrical field, then the stretching bands, that is symmetrical stretching, will resulted in the bond elongation. That means there will be a polarization within this hydrogen bond, and for this we can say that hydrogen molecule will show Raman activity. That means these stretching bands will correspond to a Raman peak in the Raman spectrum. So we can say that H2 molecule does not show any IR activity but will be Raman active. For the second case we can clearly see that there is a dipole moment within the molecule, so it will be IR active, but we have to identify the IR inactive molecule. So this is not correct. And for the second case also, it is also IR active, so it is also not correct. And for the CH2 case, it is quite similar to carbon dioxide, and in carbon dioxide the symmetrical stretching will be IR inactive, but Raman active, but the asymmetrical stretching or bending vibration will be IR active and Raman inactive. So it is also not correct, since some vibration of this molecule is IR active, but we have to identify the IR inactive and Raman active molecule. So it is also not correct, and first option is the correct answer. Now this is a problem related to hydrogen like atom, and here it is given we have to identify the number of degenerate spatial orbitals of a hydrogen like atom with principal quantum number n is equal to 6. It is a very easy question, that is for hydrogen like atom problem, the number of degenerate orbital, that is degeneracy, for a given state, that is given quantum number, principal quantum number, will be is equal to n square. If the value of the energy state, that is principal quantum number, is given, then we can easily put the value of n and we can get the degeneracy or degenerate orbitals. Here the value of n is given 6, so degeneracy or degenerate orbital will be 36. So option number 4 is the correct answer. So let's say next question. This question came from dilute solution, and we have to tell about the condition from which we can identify the value of lambda 0, that is equivalent conductance at infinite dilution of a strong electrolyte. Now the variation of equivalent conductance or molar conductance of a solution is related with the concentration of that solution is like this, and this equation is known as Debye-Huckel-Onsager equation. And from this equation we can see that equivalent conductance or molar conductance, it is equivalent or molar conductance, decreases with increasing the concentration. That means in other way we can say that equivalent conductance or molar conductance increases with increasing dilution. Increasing dilution means decreasing concentration. And if we plot a graph for a strong electrolyte, that is lambda equivalent on the y-axis and in the x-axis root over of concentration, then for strong electrolyte the graph will be like this, that is it is a straight line, and at the infinite dilution, that is when C is equal to 0 or root over of C is equal to 0, then from the intercept we can get the value of lambda 0, that is equivalent conductance at infinite dilution. Since if we put in place of C is equal to 0, that is at infinite dilution, then from this equation we will lead that lambda equivalent is equal to lambda 0. That means at infinite dilution the equivalent conductance is equal to lambda 0. So equivalent conductance at infinite dilution for a strong electrolyte can be obtained from a graph of lambda versus root over C. So option number 2 is the correct answer. This graph is for strong electrolyte. And if you want to know the graph for weak electrolyte, then just for discussion I am telling here, it is like this. Here you can see that there is a sharp increase in the equivalent conductance at infinite dilution. So it is difficult to calculate the lambda 0 value for a weak electrolyte from this graph, that is lambda equivalent versus root over C. It is for weak electrolyte. So for this, to calculate the lambda 0 value for a weak electrolyte, we have to use Polymer's equation. That I am not telling here. So next see another question, and this is from polymer chemistry. We have to identify the relation between number average molar mass and weight average molar mass for a monodisperse polymer. That is polydispersity index is related with the weight average molecular mass and number average molecular mass like this. And for a monodisperse polymer, polydispersity index is equal to 1. So it is very easy question and it is for 2 marks. So we can solve this equation and we can get that weight average molar mass is equal to number average molar mass. So option number 4 is the correct answer. And it is also a very easy question. We have to tell about the stability of a lyophobic colloid, that is the reason for the stability of a lyophobic colloid, and it is due to the electrical double layer at the surface of the particles, and it is not for van der Waals force between the particles, small particle size or shape of the particles. It is mainly due to electrical double layer in the solution of a lyophobic colloid. And here it is little tricky question. You have to apply the correct equation to identify the relation of enthalpy and this factor. You can write from the Gibbs equation that G equal to H minus Ts, and we can solve it. H is equal to G plus Ts, and now to replace the G in terms of mu, that is mu is chemical potential, it is chemical potential of ith particle. Now the relation between chemical potential and Gibbs free energy is like this, that is the free energy change of a system by adding Ni number of molecules is corresponding to chemical potential of the system. So from this we can write G is equal to mu I Ni, and the total G of the system is equal to summation over mu I Ni. So we can replace the G term here, that is summation over mu I Ni, and this term remains as it is. So we can see that enthalpy, H is the enthalpy of the solution or enthalpy of the system. So enthalpy is related to Ts plus mu I Ni. So we can see that option number 2 is the correct answer. And this is the last question of this discussion. From here we can see that we have to identify the concentration of I in this consecutive reaction applying steady state approximation. Steady state approximation tells us that the concentration of an intermediate in a sequence of reaction or in a consecutive reaction is independent of time. That means the rate of formation of the intermediate is equal to rate of decomposition of that intermediate. That means in simple word we can write that the concentration of I, change of concentration of intermediate with respect to time, is equal to 0. This is the formula, or this is the concept for steady state approximation. That means as the intermediate is formed in a step, it will readily decompose to product or other intermediate. And if we apply the rule for these two conditions, we can write that di by dt, we can write for the first step it is equal to k1 into a, and in the second step since I is decomposing, so there will be minus, and it is equal to ki k2 into I, and it will be 0. So we can write here this thing, and if we solve it we can get from this the value of concentration of intermediate I, and it will be equal to k1 by k2 into concentration of A. So we can see that option number 4 is the correct answer. So that's all for this discussion. Thank you for watching, and if you like this video then please share it with your friends, and if you are new in this channel then please subscribe to my channel Chem Analysis to get such question answer solution video or other topic in future. Thank you once again.